Let us start. Yeah, good evening. So we'll be discussing the vertex flow. Do you have any questions from the yesterday's class? Any questions from yesterday's class? Okay, great. So let us discuss one more problem so that actually you will get a great clarity on this particular topic. Then note down this problem. 2 point vertices of strength K are situated at plus or minus A at plus or minus A comma 0 and a point vertex of strength minus K by 2 and a point vertex of strength minus K by 2 is situated at the origin. Situated at the origin. Show that the fluid motion is stationary and find the equations of streamlines. Find the equations of streamlines which passes through the stagnation point. Points, meet the x-axis at plus or minus b comma 0, where 3 root 3 into b square minus a square whole square is equal to 16 a cube b. So this is the problem statement. Just read the problem statement carefully and try to understand. 2 point vertices of strength K are situated at 2 different locations. So this is one location and this is another location. Let us say this is the origin. So this point is origin and this is of strength K and this is also of strength K and this is at minus A comma 0 and this is at plus A comma 0 location and this is the origin 0 comma 0 where at this particular point minus K by 2 strength. So there is one more vertex. Got it? And then so is situated at the origin. Show that the fluid motion is stationary and find the equations of streamlines where which passes through the stagnation point. There are 2 different aspects here. So we have to prove that the fluid motion is stationary. So if the fluid motion is stationary, then these vertices will not move from that particular location. That means when there is a curl that is happening, all the fluid particles, right, are getting influenced because of the curls. Now the effect of all the vertices together, if it is coming out to be a stationary, then we say that there are vertices that are rotating there, but the fluid will be stationary there. Now, this we will be proving based on the condition that, so because of the effect of these two vertices, if this particular vertex is stationary, and because of these two, if this is stationary, and because of this one and this one, if this is stationary, then we say that the fluid is stationary. Got it or not? So the way we will be finding out here it is, so we have to identify the complex potential of these two vertices, and which will be having the effect on this is nothing but the complex potential at this particular point. Because of these two vertices, we will have to find it out. And then there, the velocity actually we have to be proved to be 0 for this particular vertex. Then actually we say that the fluid is stationary because this vertex is stationary. And same is the case, you have to prove for this one and we have to prove for this one. But for in this case, we'll prove for this, and then we can say that similar thing is happening for both the things. Hence the fluid is stationary. Got it or not? So that is the first part of it. So we have to prove that none of the vertices are moving from their respective locations. So that is one aspect. And another is find the equations of these streamlines. Now actually these fluid particles, right? So the fluid is stationary. That means those vertices are located there only, but the fluid is moving, right? So because this is a curl that is happening here. This is a curl. Now actually because of these curls, so there will be some stagnation points where the fluid particle stays then and there only. That means if this fluid is rotating like this, and if this fluid is rotating like this, and then at one particular point, so these two will compensate together, and then it will try to stay the fluid particle there itself. Now, those are the lines that you will have to identify where the fluid is staying as it is. And that's what we call as the stationary points. So, stagnation points. For that, what we can do, we will have to find out the complex potential randomly at any location. And then the derivative of the complex potential is nothing but U minus IV is nothing but minus dW by dZ. Right? So U minus IV is nothing but minus dW by dZ. And if this derivative is coming out to be 0, and those are the points actually, we say that the stagnation points are where there is no velocity, because this is nothing but the velocity or the complex velocity. Got it? So dW by dZd. So for that actually we will have to find out the W value at any random location, which is nothing but the effect of all the vertices together at this particular point. Here actually we will have to find the complex potential, for which the derivative has to vanish to find out the stagnation point. Now those stagnation lines, so those stagnation points, suppose if this is a stagnation point, if there is a streamline that is passing through like this, and this point actually trying to cut at one location, that is at plus r, so if this is cutting at this particular point, minus b, so comma 0. So this is passing through b comma 0 and minus b comma 0. Those are the streamlines we will have to identify. Those streamlines are given by the condition given by this one, this equation. So if the stagnation points are passing through some point, these are cutting the x-axis at plus r minus b comma 0, then the relation of the streamlines is nothing but this one. Got it or not? And this is the entire problem statement that you will have to solve it. So solve this one. I hope you got a fair clarity on this particular problem statement. So do you have any questions on problem statement, understanding this problem? Any questions on the problem statement? Clear? Okay. So now actually I will give you 5 minutes time. You try to solve this problem on your own first. Then actually I am going to solve it for you. First you give it a try. So are you on track? See this. So here actually, because of these two vertices, let us say the complex potential at Z. So the complex potential at Z is given by W is equal to Ik by 2 pi times log of Z minus A. So that is because of this vertex, the complex potential at this location. So that is Z minus A plus, so Ik by 2 pi I have taken out, then this will be log of Z plus A, and then because of this it is minus Ik by 2 into 2 pi. So that is minus 1 by 2 times of log Z. So this is the total complex potential, right? Now this complex potential, so this is the total complex potential. You can put it in a simpler format, Ik by 2 pi times, so this is log Z square minus A square minus half log Z. So this is the complex potential. Now if you want to prove that this particular particle or the fluid particle which is present at Z is equal to A, if it is stationary, so that actually you can prove that the fluid is stationary. For that, what you can do, you have to identify the complex potential at this particular point Z is equal to A. But at Z is equal to A, there is a vertex that is present. Now yesterday I explained that because of this vertex, the fluid particle at this particular location is not getting influenced. That's why you have to subtract the complex potential of this part, and then you have to consider all other vertices together, the influence at this particular point. So W dash, let W dash be the complex potential at Z is equal to A and is given by W dash equal to, you have to remove the effect of Z minus, so Z is equal to A, that is you have to remove this particular term. So then it will be Ik by 2 pi times of log of Z plus A minus 1 by 2 times of log Z. So this is the complex potential at the point A comma 0. Now this vertex actually we have to prove that this is stationary. For that actually take the derivative of this, dW dash by dZ is nothing but Ik by 2 pi times 1 by Z plus A minus 1 by 2Z, and then taking at Z is equal to A, so this is the velocity at Z is equal to A because of the effect of this particular complex potential, which is nothing but the effect of all other vertices together, that is this one and the middle one. So if you put Z is equal to A, then this is coming out to be 0. Now what it implies for us, so the complex velocity is coming out to be 0. So the complex velocity is nothing but minus u plus iv. So this is being 0, the vertex at Z is equal to A will not move. So this is the combined effect of it. Similarly, we can prove at Z is equal to A, Z is equal to minus A and Z is equal to 0, the vertices will not move. Will not move. Hence the fluid is stationary. This is one part of the problem statement. Got it? W dash is nothing but the complex potential at this particular point. So this is the location of W dash. Understood, Samrin? Okay. I hope you understood this part of the problem statement. And then this you can further simplify. So from this actually you can even prove that dW by dz is nothing but the complex velocity of the combined effect of all the vertices together. That is, this particular location, if the complex potential is W, then the fluid particle at this particular point, whose complex velocity is given by dW by dz, which is given by minus u plus iv, and this is equal to the derivative of this. This is ik by 2 pi times of 2z by z square minus a square minus 1 by 2z. So this is dW by dz, and this is dW dash by dz. That is the difference. And then if I equate this to 0, then those are the locations of the stagnation points for us, because this is the location of the complex potential now. So if I make this velocity being 0, then it is nothing but the stagnation point there. Got it or not? Got it? Okay. Fine. So you note down this. We are going to take out the second part of the problem statement. Okay. Then the complex potential W is equal to Ik by 2 pi times of log of z square minus a square minus 1 by 2 times of log z. Now this is nothing but the complex potential, which you can express as 5 plus I psi. Now 5 plus I psi, this you can further simplify as Ik by 2 pi times of this, if you write z as x plus iy, and this is log of x plus iy whole square minus a square minus 1 by 2 times of log of x plus iy. And this one Ik by 2 pi log of x square minus y square minus a square plus 2xy into I minus 1 by 2 log x plus iy. And then this is Ik by 2 pi. Then if I put this entire thing in r e power I theta format, so r e power I theta, where r is nothing but the square of, which is nothing but the magnitude, the square of this plus square of this under root. That is x square minus y square minus a square whole square plus 2xy whole square, and then whole power 1 by 2 into e power I theta 1. I call theta 1, where theta 1 is tan inverse of 2xy divided by x square minus y square minus a square. So this is how actually you can put this one. And then log of minus half log of x square plus y square under root e power I theta 2, where theta 2 is equal to tan inverse of y by x. Now why I am putting this format is, in this way I can get, yeah, so in this way, I can get, so the real part and imaginary part separately. Now here, log of the product of 2 will be log A plus log B. Then this part, log of e power I theta 1. So then it is come, I theta 1 will come in front of the log. Then log E is 1. So I theta 1. So I into I outside. So it will become minus 1, which will become the real part. But this part is nothing but the imaginary part. So from this, if you can separate the psi value, which is nothing but the imaginary part will become, this is k by 2 pi times of log of x square minus y square minus a square whole square plus 2xy whole square whole power 1 by 2 minus 1 by 2 times of log of x square plus y square whole power 1 by 2. So this is the real, so imaginary part of it. So this is nothing but the streamlines equation or the stream function. Got it? This is the stream function. Understood? Understood or not? So this is how actually we found the stream function. So from these two, this power 1 by 2 and power 1 by 2 can bring it to here into 2. So 1 by 2. So if you take 1 by 2 out, k by 4 pi, if you take out, then this will be log of x square minus y square minus a square whole square plus 2xy whole square divided by. So this is 1 by t is taken out, minus will come. So then it will be x square plus y square whole power 1 by 2. So this is how actually you are going to get it, the psi value. Understood? So this psi value, we can treat this as k by 4 pi times of log of something is there. Now, for a random constant of psi, which we call as the stream function at that particular position. That is, if you select a random constant of c, so if c is equal to, psi is equal to constant, will give the streamlines. Right? So psi is equal to constant will give the streamlines. This is a master stream function. For different values of psi, you are going to get different set of streamlines. Right? So this c value, now actually we treat this as constant, and let us say this constant is k by 4 pi times of log d, some random constant d. This is an arbitrary constant d. So this way, I can relate directly this arbitrary constant to this function straight away, so that I can avoid log in between, so that I can avoid my confusion in the solving the problem. Got it or not? Understood? Not clear. See this. Here actually, till this point, separation of these streamlines actually, I hope everybody understood, right? Real part and imaginary part is separated, and I have written the imaginary part separately as the psi. So psi is equal to constant will always give the streamline. So the function psi is a function of x comma y comma z, right? And then if I equate that to some constant, this is nothing but the streamlines equation. So this function is called the stream function, and if psi is equal to constant is equated, then we call that as the streamlines. So for different values of this constant, we are going to get different set of streamlines. So this is like solution of the differential equations. Actually, we are putting arbitrary constant. For different arbitrary constants, you are going to get a different solution, right? So it is exactly that manner. So suppose if the fluid is continuously flowing like this, then one layer actually you will have the streamlines, and below actually we will have another set of streamlines, but at a different value or at a different location. So that is psi is equal to constant 1, that is at this level, and psi is equal to constant 2 at this level, and psi is equal to constant 3 is at this level. So for different levels actually you are going to get different set of streamlines, and each set we call as the streamlines. In general, if I take this out, then we call this as the stream function, but if I equate to some constant, we give the streamline. So that's why psi is equal to constant is a rule to get the streamlines from the stream function. Got it? Understood or not? So rather than, so now I know that this is anyway constant. So if this is a random constant which I am selecting, I selected this random constant as, so k by 4 pi times of log c. Like this actually I have selected. Instead of c I used d, that's it. So this is a random constant. So instead of c I selected as k by 4 pi times of log c, which is nothing but where c is the arbitrary constant here. Why I have selected this method of finding out the arbitrary constant is, I can avoid the confusion of k by 2 pi times of log, so which is there on the right side, so that I can remove that factor if I put that in, if I incorporate that into the constant part. Clear now? Got it or not? Okay, great. So once you understand this aspect, then actually, so I hope you noted down. Everybody noted down? Noted? Okay. Now, the simplified form of this is, so this equation can be simplified as now, so it is x square minus y square minus a square whole square plus 2xy whole square is equal to x square plus y square whole power 1 by 2 times of some random constant d. So this is the random constant d. Got it or not? So this is how actually we can simplify that equation. So I have avoided k by 2 pi factor and I have avoided log, and then straight away equated this by this is equal to d. So this d value we need to be finding out based on the initial conditions. Those initial conditions what he has given is, he said that the stagnation points, so the streamlines that are passing through the stagnation points are intersecting with respect with the x-axis at plus or minus b comma 0. That is the statement he made. Now from that actually, what are the stagnation points? Where are the stagnation points that are occurring? That we will be finding out with the help of this one. So this is nothing but, if I equate to this 0, then I am going to get the value of the location of the stagnation point in the complex form. Now let us take this I equated to 0. So the location of the stagnation points will be dw by dz equal to 0. So dw by dz is nothing but the complex velocity. Now dw by dz, I got that ik by 2 pi times of 2z by z square minus a square minus 1 by 2z, and this equated to 0. Then it implies 2z square 4z square minus z square plus a square equal to 0, or 3z square equal to plus a square equal to 0, or z is equal to plus or minus ia by root 3. So these are the locations of the stagnation points, right? So plus or minus ia by root 3 is nothing but 0 comma a by root 3. So 0 comma minus a by root 3 are the set of the stagnation point locations. So this equation, whatever we have got, this point is nothing but the location of this stagnation point. If I substitute this value in this equation, I am going to get the specific constant, that is d value, in terms of a. So if I put this point in this particular equation, then I am going to get the streamlines that are passing through the stagnation point. So those streamlines will be, if I substitute there, x is equal to 0 and y is equal to a by root 3, then 0 minus a by 3, a square by 3 minus a square whole square plus 2 times of 0 whole square plus 0 equal to 0 plus a square by 3 whole power 1 by 2 into d. So this value is coming out to be, so this is 4a square by 3 whole square is equal to, so a square by 3 whole power 1 by 2. This is a by root 3 into d. So this is 4a square by 3, 16a square by 9 is equal to d into a by root 3. So this a will cancel and this is 3 root 3 times. Then what we are going to get it is d is equal to 16a by 3 root 3. So this is the arbitrary constant actually which we found. So this arbitrary constant is nothing but, so if we substitute it here, that is x square minus y square minus a square whole square plus 2xy whole square is equal to 16a by 3 root 3 times of x square plus y square whole power 1 by 2. So this is equations of the streamline passing through stagnation point. Passing through the stagnation point, right? So I hope you understood this. Yeah, I think you are correct. So 16 a power 4. So a power 4, 1 a will cancel, this will be a cube, like that. Got it? Yeah, that's correct. Understood? Noted down? Or do you have any questions till this particular point? Any questions? So this is a simplification, nothing more than that. So substituted the stagnation points and then we got the arbitrary constant value and we have written the accurate equation. So by replacing this arbitrary constant. Now the further extension of this particular problem statement, what he said was the streamlines which are passing through the stagnation point are intersecting with respect to the x-axis at plus or minus b comma 0. That means, so if x is equal to b and y is equal to 0, then actually what is this relation is going to be? That's what actually we need to be putting it. That is the final format. So we have got x square minus y square minus a square whole square plus 2xy whole square is equal to 16a cube by 3 root 3 times of x square plus y square whole power 1 by 2. So these streamlines are passing through plus or minus b comma 0. Hence, if we substitute this point in the above equation, then if we substitute this, then so x become b square minus a square whole square plus, so y equal to 0. So this will anyway 0 plus 0 is equal to 16a cube by 3 root 3 times, so b square whole power 1 by 2. So these two will cancel. Then b square minus a square whole square is equal to 16a cube by 3 root 3. I think so. This is what he asked us to prove. Got it? Yeah, that's correct. Got it? Any questions on this? Anjali, what is your question? So this is what actually he asked us to prove. Yeah. Yeah, 16a cube b, exactly. Yeah, that's correct. Fine. So, but actually, I hope you understood the problem, how we are going to deal with. Got it? Yeah. So, the summary is, whatever the problems we are going to deal in case of vertices or the sources or the sinks. So, this is actually covers the major portion of fluid dynamics topic, where you can expect the questions only from these regions. So that is, one is the vertex flow, another is the two-dimensional flow. These are the locations we can expect questions, but both the questions are easier. Easier, I mean, so the mathematical model of the fluid flow is easier, but the complexity is simplifying that mathematical model so that you can get a valuable inference. So that is with the help of complex analysis, which you have to do it, and that will be very, very tough. So that part you need to practice. That means essentially falls down to the same complex analysis process, nothing more than that. But this is very, very important section of the syllabus. Got it? Most of the times the questions were asked from these sections. Any questions on this? Got it? Okay. So note down one more. So the image system of a vertex. So this is as if like in case of sources and sinks, actually the way we have modeled the images, right? Exactly the same process follows even here also. Suppose if there is a circular cylinder in an infinite cylinder like this, then let us say this is the center and there is a vertex of magnitude k here, of strength k, which is located at a distance of r. Let us say this is the distance of r. Let us say the radius of this particular cylinder is a. Then, so because of the presence of one vertex, for the accurate mathematical model of the image system, what you need to do is, so if this is plus k, then you have to introduce one more vertex of magnitude minus k at this particular point and minus k at this particular point. So these two locations actually we have to introduce one more vertex of opposite magnitude there. Then this system together will form the image system of a circular cylinder, right? Now, what is the location of this? This is, if this is A and this is R, then A square by R is the other location. Got it? A square by R. Suppose if the vertex is present outside, let us say here actually there is a vertex of magnitude k, then you have to introduce plus k magnitude here and you have to introduce one more minus k at this particular point, and this location is again A square by R, but this is R in this case. So this is capital R. If I say this is capital R, this is small r. So if you notice capital R value is more than the radius, then obviously if I divide with the more than the radius value, it is going to get a value which is less than the radius. That's why it will be inside. Suppose if this is the radius value is less than the this cylinder radius, then 1 by r of this one is giving the value which is more than the a value. That's why it will be outside. So for a system, so this is what we call as, so the image location of the circular cylinder. Got it? Understood or not? So why we are discussing? Yeah. See this. I hope you understood the image system, right, Anjali? So image system is nothing but to make sure that the fluid flow analysis will not go wrong. We will be introducing extra sources or the sinks depending upon the requirement, so that our mathematical model will be accurate. That means why we are getting the problem of non-accurate mathematical model is, so you will be modeling these stream functions or the complex potentials, everything in the presence of infinite fluid. But what if there is a hurdle there? Now this infinite model of whatever the complex potential you have put in, that will not holds good in the presence of the wall. So that's why, so what you are saying is, you are saying that there is a streamlines that are passing through like this. Now there is a flow. The streamlines are passing through like this. So these streamlines are passing through like this, provided if there is no wall like this, If there is a wall, then actually obviously the streamlines will not cross this, right? If there is a wall hurdle, then it will not cross. Obviously, the mathematical model, so if I ask you at this particular location what is the fluid flow direction, then obviously you will be tempted to say that this is the direction of the fluid, but ideally it's not. For that, what we are doing is, we are putting a image system. Image system is nothing but, suppose if this fluid flow is just because of the presence of a source of magnitude m here, then you have to assure that there is one more source of magnitude plus m on other side, so that this also will try to push the water like this. This will try to push the water like this, and both the places together, it will come out to make this particular point, which is nothing but the fluid flow will not cross this particular wall. So that method we call as the image system. Got it or not? Introducing this source is nothing but the image system of this particular wall. Got it? Exactly in the similar manner, what if there is a circular cylinder like this? So if there is a circular cylinder like this, and there is a source at this particular point. Now to analyze accurately, what you are doing is, there is a method for each shape, the image system is completely different. That is dependent on the shape. Suppose if there is a circular cylinder, the method of image will be completely different. If the wall is of this particular shape, then the method of image will be completely different. So this case also I have explained. If there is a source that is present here, you have to put an opposite source here, and you have to put one more here, and you have to put one more here. Now this is another system. That is, if there is a L kind of shape is there, the wall, then actually the source presence here will force you to have one source here, one source here, and one source here. Now all the sources together will make the image system. Got it? But of opposite magnitude. This one and this one will be the same magnitude, and this one will be the opposite magnitude. Then it will make our analysis more accurate. So exactly in the similar manner, in case of the presence of a circular cylinder, if there is a vertex of magnitude k that is present here, then for the image system, for a more accurate mathematical model, you have to put into the image system. That image system will be, if there is a vertex at this particular point, you have to place one more vertex of opposite magnitude here. So this is a vertex, not a source. So opposite magnitude here, and this is of minus k, and is located at a distance of a square by r, where a is the radius of the cylinder and r is the location of the first vertex. And then you have to introduce one more vertex, which is opposite to this one at this particular center. Then only these three together will make our analysis accurate, which will make the streamlines to pass through tangential to this particular circular cylinder. Got it or not? Because within this particular one, if there is a curl, obviously the water will flow tangential to this one like this. So it will not have the flow outside. So that's what we are trying to model it here. Got it or not? Here, any questions on this? So you have to introduce, for one particular vertex k, you have to introduce minus k here and minus k here. So one minus k is completely at origin, and one is outside the cylinder at a distance of a square by r. So this you have to note down. And take this other case. Suppose if there is a vertex outside, and then there is a closed cylinder that is present here, then for the accurate model of the flow, you have to model inside there is one vertex, which will be given by exactly the same distance a square by r. But in this case, r being the outside, a square by r will come inside location. So that's why this will be again a square by r, and this is also a square by r. But here r is less and here r is more. That is the only difference. And there is one vertex at the center. We have to model it exactly the same as the outside one. Got it? So this is the mathematical model or the image system of a circular cylinder. Now actually, based on this, actually in UPSC, there was one question actually which was asked. So exactly the same case actually he asked. So you note down that problem. You try on your own this particular problem. In case if you are not able to solve, I am going to solve it tomorrow. And then there will be only, so after tomorrow there will be only one class I will be giving to this fluid mechanics. So after that we will be done with fluid mechanics. So note down this. This was given previously in UPSC. When a pair of equal and opposite rectilinear vertices, when a pair of equal and opposite rectilinear vertices, equal and opposite rectilinear vertices are situated in a long circular cylinder, are situated in a long circular cylinder at equal distances from its axis. At equal distances from its axis. Show that the path of each vertex, show that the path of each vertex is given by the equation r square sin square theta minus b square into r square minus a square whole square is equal to 4a square b square r square sin square theta, where theta being measured from the line through the center perpendicular to the join of the vertices. So this is the problem statement what he asked for, and then so here actually there is a circular cylinder like this, and then let us say this is the center. So the axis of the cylinder will be exactly perpendicular to this one. So this is the axis of the cylinder. So two different. So when a pair of equal and opposite vertices. So suppose if I call this as plus k, and then there is one more minus k at this location. So two different vertices. So a pair of equal and opposite vertices are located. Now so this is minus k. So if there is a pair of vertices, then obviously the image system of this particular plus k will be, so you have to join like this, and there is one minus k which is located at this point, and then the radius of this. So let us say this is the radius a, and then here actually there is one vertex which is located. Let us say this distance is r, then obviously this will be a square by r location, and here also. So this is one more location. If this is minus k, then you have to introduce plus k here, and then correspondingly plus k you need to introduce here. Because of this you need to introduce minus k here and minus k here. Now these two together will cancel out. Got it or not? Understood? So here actually what he said was, this is an angle theta, where theta is described such a way the perpendicular to the line of joining these two vertices. So here actually, so you have to draw a line like this, exactly in the middle of the line you are drawing one line. So from this actually one vertex is at plus theta, obviously the other vertex is at minus theta. So at minus theta there is a minus q, and at plus theta there is one plus q. Obviously the image system is minus k here and plus k here. So minus k here and minus k here, and for minus k the image system plus k here and plus k here. These two will cancel it anyway. So that's why you don't need to consider these vertices. So you have to find the mathematical model of all the four vertices, this one and this one, this one and this one. Got it or not? Understood? And then what he has given is show that the path of each vertex is given by the equation this one. So this is the path of the vertex. So path of the vertex we mean, so you have to find out the complex potential at any of one vertex. Suppose if you take this as the complex potential location, you have to consider the effect of the complex potentials of this one, and this one, but not this one, because you are trying to find out the velocity of the vertex itself. That means the fluid particle that is present within this particular vertex, you are trying to find it out, where this vertex will not have effect on that. Got it or not? So this is a simple problem only. So you have to find out the complex potential at this particular location, and then from there separate the real and imaginary part. You are going to get the stream function. So that stream function we have to be separating it out. Got it or not? Okay, so you try to solve this on your own. In case if you are not able to get, I am going to explain it tomorrow. Got it? So after that, I am going to take up the viscous flow. So that will be the last part of our syllabus. Clear? Any questions? See, not very great. So actually, viscous flow will be only one class. So after that, actually, we will be finishing off this fluid mechanics. Then afterwards, actually, we are going to start with the mechanics part of it. Got it? So mechanics actually, so I think it will be somewhere around 10 classes. So after that, mechanics will be finished. Then after that, we will be starting with the fluid mechanics. So we will be starting with the partial differential equations. Yeah, partial differential equations. So there is one popular model actually. So most of the times it was asked. So I think it will somewhere around 15 to 20 classes it will take. So maximum of 20 classes for partial differential equations. Yeah. Got it? So after that, we will be finishing off all. Clear? Okay, so that's all for today. Yeah, so you try to solve this on your own. This will be easier problem only. This was given previously by UPSC. Yeah, all these classes I wanted to put at 6 p.m. itself till we finish the syllabus. Okay, yeah. So thank you. Good night.